In most years, the inner solar space receives only a few comets, but at the end of 2025, 7 significant objects are heading towards us, including the interstellar giant Tri-and/Atlas, which grows larger each day. Astronomers are mapping this unprecedented cluster. Such a sight has not been observed since modern telescopes appeared. They track the approach of these comets racing past Earth and the Sun in a narrow 6-month time window. Some predict that all this activity could even provoke solar storms, and one of these comets might flare up so brightly that we could see it with the naked eye. But why are so many comets moving towards us at the same time? And what danger or wonder might this cosmic traffic jam bring? Let's take a closer look at the rarest comet calendar of our time. 7 large comets filling the inner solar space in a single season is an almost unheard of event. In most years, astronomers can observe 1 or 2 bright comets passing close enough for detailed study, sometimes 3, if luck is on their side. But a year with 7 comets, all of which approach in just a few months, is an event that stands out even against a century of observations. Since the beginning of systematic sky observations, such as Pan-STARRS, Linear, and the Atlas project, no season has rivaled this activity. The last time the number of comets approached such figures, telescopes were still capturing images on glass plates, and most discoveries happened by chance or through rumors. Now it is important not only the total number of comets, but also that this cluster differs from the slow flow over the years. It is a concentrated influx, where each object rushes through the inner solar space in rapid succession. Some approach from the farthest borders, others return periodically, and one comet, 3-Atlas, does not even belong to our solar system. This interstellar joker would be news in any year, but combined with 6 other large comets, the chances of such an event become almost negligible. Statistically, on average, from 2000 to 2022, there was only 1 comet that reached brightness visible to the naked eye, and 2 or 3 others that could only be seen through binoculars or telescopes. There are years when we see only faint, distant comets. Even during the so-called comet reigns, when several objects pass together, numbers like 7 are practically absent in modern records. According to public records from the Small Planet Center, since the beginning of the digital age, no season has recorded more than 4 large comets with perihelion within 2 astronomical units, not accounting for the elliptical alignment demonstrated by this group. For reference, the discovery of comets has significantly increased in recent decades due to robotic sky surveys, but the overwhelming majority are dim, distant, or short-lived. Bright and accessible comets remain a rarity. The influx of comets in the year 2025 is so unusual that some astronomers describe it as a statistical anomaly, an event that may only occur once in several generations. That is why it is not just a list of objects. This phenomenon is unusual, a true storm that challenges our expectations of the solar system's usual rhythm, with many icy guests appearing almost simultaneously. Astronomers view it as a single event, with multiple acts. Attention shifted from studying individual comets to tracking their collective choreography, how their orbits, alignments, and solar encounters might interact or overlap. This rare convergence evokes both scientific excitement and public anticipation. Before delving into the details of what perihelion, upper conjunction, and alignment with the ecliptic are, it is worth noting how rarely one can see 7 large comets sharing the same scene at once. Comet C 2022. N2 Pan-STARRS opens the comet season of 2025, reaching perihelion on July 31st at a distance of 3.82 astronomical units from the Sun. Its distant orbit extends far beyond Mars, where sunlight is weak, and only the most sensitive telescopes can track its movement. Pan-STARRS sets the outer boundary for this swarm, a quiet beginning before more dramatic appearances. Then follows the C-2275 R2 Swan, launched on September 11th and racing towards perihelion. Just a day later, on September 12th, it will reach 0.5 astronomical units. The main event will occur on October 21st, when Swan passes by Earth at a distance of only 0.25 astronomical units, about 37 million kilometers. This close approach makes it an excellent candidate for observations, especially in the pre-dawn sky of the northern hemisphere. The swift movement and geometry of Swan provide a rare opportunity to study the interaction of the comet with both the Sun and Earth in real time. Comet 14. P stereo will pass by the Sun on September 27th at a distance of 0.52 astronomical units. Its orbit dips below the ecliptic plane, making observations with ground telescopes difficult. often lost in sunlight. The comet, named after the stereo mission, is best suited for observation by spacecraft. Its low trajectory offers a different perspective for solar studies. The C-2025K Atlas arrives next, reaching its perihelion on October 8th at a distance of only 0.33 astronomical units, closer to the Sun than Mercury has ever been. This close passage to the Sun means that Atlas will undergo rapid changes, making it a key object for observing emissions and tail development. Its proximity to the Sun places it at the center of the swarm's activity. Comet 3I Atlas, an interstellar visitor, will reach its upper conjunction on October 21st, passing behind the Sun from Earth's perspective. Perihelion will follow on October 29th at a distance of 1.36 astronomical units, just inside Mars's orbit. With an inclination of about 5 degrees, 3I Atlas move close to the ecliptic, sharing the sky with planets and other comets. For several days, both I-Atlas and SWAN will occupy important positions for solar interaction studies, although neither will be easily visible. Comet C-2025 A6 Lemon will reach perihelion on November 8th at a distance of 0.53 astronomical units. Its orbit allows it to be observed in the evening sky after sunset, providing one of the most accessible opportunities for observing a group of comets. Forecasts indicate that it may reach brightness of 4 or possibly even 3.5 stars, making it visible to the naked eye for northern observers in early November. The comet will complete its journey and reach perihelion on December 19th at a distance of 2.12 astronomical units from the Sun. As a periodic comet, it is less bright and distant, yet its appearance highlights the busyness of the inner solar system by the year's end. The orbit of each comet, the date of perihelion, and its connection to the ecliptic create a tightly packed calendar, setting the stage for the solar interactions that will follow. The tails of comets are not just cosmic streams. They are living records of invisible forces acting in the solar system. As the comet approaches the Sun, solar radiation heats its core, releasing gas and dust that form two distinct tails: a wide pale dust tail and a narrow electric blue ion tail. The ion tail, in particular, is a straight line towards the Sun's magnetic field. It consists of charged particles blown away by the solar wind, a continuous stream of plasma and magnetic fields spiraling out from the Sun at hundreds of kilometers per second. However, the ion tail is not constant. It can break in the blink of an eye, what is called the event of tail disconnection. The physics of this phenomenon is based on magnetic recombination. When a comet moves through the solar wind, it sometimes encounters sharp changes in the interplanetary magnetic field, such as during coronal mass ejections or crossing the heliospheric current sheet. These transitions are not gentle. The magnetic field can shift by 90 degrees or more in just a few minutes, and at that moment, the comet's plasma environment fails to adapt. The old tail breaks away, drifting into space, while a new tail begins to form, perfectly aligned in the new direction of the solar wind. One of the most impressive examples was the event in April 2017, when the Stereo spacecraft observed a coronal mass ejection colliding with Comet NK. The ion tail was neatly severed, creating a visible rupture near the nucleus, while the old tail continued to drift. This was a training example that matched magnetohydrodynamic simulations, almost frame by frame. Such events are not uncommon during solar maximum. With several comets approaching the ecliptic at the end of 2025, the likelihood of observing a tail disconnection is higher than ever. The dusty tail, unlike the ion tail, is less affected by these magnetic storms. He is governed by sunlight and gravity, not magnetic fields. Only the most powerful coronal mass ejections can alter or shorten the dust tail, usually tearing part of the coma or changing the direction of the ejection. For most observers, the sharp breaks in the ion tail and its subsequent growth are hallmark events, vividly demonstrating the restless energy of the Sun, written across millions of kilometers of space. Solar physicists observe the comet swarm with interest and concern, not just for the spectacle. Behind the scenes, a tense discussion unfolds about what the close passes of comets might mean for the behavior of the Sun. Some research groups, especially the NASA CCMC modeling team, claim that a sharp surge of plasma and dust from comets, particularly those moving along the ecliptic, can actually push the Sun towards more frequent or intense eruptions. Their simulations show that when an active comet crosses the heliospheric current or passes through a coronal mass ejection, the magnetic geometry can change rapidly, sometimes causing a classic tail disconnection event. In these models, the lines of the Sun's magnetic field wrap around a comet, and if a coronal mass ejection passes at the right angle, the ion tail can detach, sometimes in just a few minutes. CCMC's MHD models suggest that with multiple comets, especially during solar maximum, the likelihood of observing dramatic tail disconnections increases, and an excess of plasma may even contribute to new instabilities in the solar wind. However, not everyone agrees with this. The teams of the Solar Orbiter and Parker Solar Probe refer to their own data, claiming that most tail disruptions are much less pronounced than predicted by models. They collected many small fractures and bends in the tails of comets, which never lead to complete outages, even during strong coronal mass ejections. Their field measurements show that small-scale turbulence, micro-reconnection, and background variability of the solar wind can play a significant role, sometimes even greater than powerful coronal mass ejections. In their opinion, the true driving forces are the sun's own magnetic cycles and large-scale changes in the magnetic field, while comets act more as passive traces than active agents. They warn against overestimating the risk to satellites or energy grids, noting that even during the Encke event in 2007, the operational impact was minimal. Nevertheless, with the expected level of coronal mass ejections ranging from 2 to 5 per week during the solar maximum in the year 2025, both sides agree on one thing. It is a rare opportunity to test their theories in real time. Space weather specialists intensify monitoring, while citizen scientists prepare for a global campaign. If a significant tail disconnection occurs during comet observation, observers, from home telescopes to spacecraft, will be ready to capture the event. So far, the debates have captured everyone's attention. Every new coronal mass ejection, every strange tail movement can change the dynamics in this ongoing scientific dispute. When astronomers first plotted the orbit of the comet Tri, the numbers did not fit the known patterns of familiar comets. Its trajectory is hyperbolic, with an eccentricity significantly greater than 1, meaning it not only visits the solar system, but passes through it, never to return. This already sets it apart from others. Only 2 objects, Oumuamua in 2017 and Borisov in 2019, were confirmed as interstellar before it. But the Atlas differs in other parameters. Early measurements from the Hubble and James Webb telescopes show that the comet's core ranges from 320 meters to 5.5 kilometers in diameter. However, the coma, a cloud of gas and dust it sheds as it approaches the sun, has already reached a width of about 700,000 kilometers. This is nearly the size of Jupiter, and it continues to expand each week. Unlike most comets that spend millions of years in the distant corners of our solar system before making one pass near the sun, the Atlas comet came from much farther away. It was likely ejected from another star system, carrying material formed in a different cosmic environment. Its composition is also distinctive. Spectra show that the coma mainly consists of carbon dioxide and other volatile gases, while water vapor is rarely found, and cyanide is detected only in trace amounts. These chemical traces are rarely found in such abundance in local comets. The object's motion also indicates its origin. He entered the solar system at a steep angle, barely touching the ecliptic at a distance of only 5 degrees, moving so fast that there is no doubt of his extraterrestrial origin. The scientific value of this discovery is enormous. Each observation allows us to compare the building blocks of distant planetary systems with our own. It's not just about chemistry. When Atlas orbits the sun, it leaves behind a trail of dust and debris that Earth will cross in the year 2026. This is a rare opportunity for planetary defense teams to observe interstellar material up close. The story of Comet 3I Atlas is still unfolding, but it is already rewriting our understanding of the boundaries of our solar system. From late October to early November 2025, the sky opens a rare window for comet watching. No specialized equipment is needed, just a clear gaze and a bit of patience. The show will begin before dawn on October 21st, when Comet C2025 R2 Swan approaches Earth at a distance of about 0.25 astronomical units. Even through modest binoculars, the tail of the Swan will stretch an astonishing 2.5 degrees, 5 times wider than the visible disk of the full moon. Its head will shine with a magnitude of 6 to 7, dimly, but accessible to those willing to rise early and watch the southeast sky. For most northern latitudes, Swan will rise almost 40 degrees above the horizon in civil twilight, making it an ideal target for pre-dawn observations. Meanwhile, 3I/Atlas will set behind the sun at the moment of greatest conjunction. While ground-based telescopes lose sight of it, the action shifts to the network. Solar observatories, such as the LASCO C3 coronagraph on SOHO, continue to observe, capturing the 3I Atlas and sometimes Swan as faint moving dots against the sun's outer atmosphere. These broadcasts are available to a wide audience. Anyone can join in the search for sudden changes, flashes, or even events related to the tail disconnection caused by a solar storm. By early November, Comet C-2025A6 Lemon will become the star of the evening sky. The forecasts indicate that the brightness of the comet will be about 4 magnitudes, possibly even 3.5, allowing it to be seen with the naked eye from dark places, especially for those in the northern hemisphere. The Lemon Comet will be low in the southwest after sunset, its coma and tail shining brighter each night as it approaches perihelion on November 8th. For many, this will be the easiest comet to observe in recent years. Whether you use binoculars, a telescope in the backyard, or just your eyes, it's time to go outside and see how our solar system moves. The best nights for observations are October 21st, when the Swan Comet will make its closest approach, and from November 6th to 12th for the main display of the Lemon Comet. For comets hiding near the sun, global coronagraphs provide the opportunity to observe with just a click in the browser. Predicting comets is a lesson in humility, regardless of the volume of incoming data. Each year, brightness forecasts can fluctuate by 2 magnitudes or more. A comet expected to shine brightly at level 3 may become barely noticeable at level 5 or 6, while a weak and unnoticed newcomer can suddenly explode, surpassing all expectations.